Okay, so this is the last lecture before Christmas break, and we should be talking about a thing called GPT. And this is, I mean, we're getting from zero to something which everybody is using almost on the, well, maybe on a daily basis, or at least have heard of that, at least. Or, ChatGPT is a successor of these GPT models, which is kind of an achievement. If you think about it, I mean, I don't know if you had some previous experience with deep learning and NLP. Some of you didn't, and now we're basically coming to the state-of-the-art models, which is kind of cool. And as you might see, like there's no magic in those models. There's a lot of clever tricks, clever ideas, engineering tricks, and a lot of compute. So let's start talking about GPT. But well, so last time we were talking about BERT. So do you remember what the BERT was? It was this transform model for learning contextualized token embedding. So what does it mean? So what does it mean if I have an input sentence, the cat said, what does BERT will give me for this input sentence? What will it learn? Well, learn. I mean, it's trained on something, but then if I want to do some, let's say, text classification or sequence labeling, BERT gives me something. You remember what the something was? Like what I'm getting here from BERT? So we have a bunch of tokens, and for each token, we're getting something. What was that? So these are these embeddings, right? I mean, we are getting contextualized embeddings. So each word, after it goes to the BERT model, it gets a embedding vector, and we have three words, so three tokens, so we're getting three word embeddings. I mean, these are some subword units, typically. Okay, so we're getting embedding vectors. So and the difference of the embedding vectors so what is the difference of word-to-vec word embeddings and those embeddings? There's a huge difference, like what they can kind of express, these embeddings. So what was there? I mean, in word-to-vec, if I ask you for a word, give me your embedding, you will always get one embedding for one token or for one word, no matter in which context the word appears, right? I mean, word-to-vec is just basically lookup table. You get it the word a bank, you get the embedding for a bank, no matter what the meaning of that is and in which context they appear. While in BERT, we're having these contextualized embeddings. So it means it takes the whole sequence into account, and then for each word gives me the embeddings. But it takes the context, which gives you different embeddings for each token in different contexts. So this is the advantage of why is it powerful. How it works internally, we'll come to that again later. I mean, maybe a little bit of recap. So, but BERT can be used for text classification. So we have this one single token called, we always edit this token called CLS, so very special token at the beginning. And this CLS token was transformed into some, again, like embedding of the whole sequence, which then we used for some classification here. So maybe through, I don't know, some projection and a softmax and stuff like that. So it's a text classification. Also, we can use BERT for sequence labeling, which means each of these tokens can be labeled somehow. So what is NER? What was that? So what is the last letter for? Something with recognition? I guess so. So the NER, the whole thing is, well, it's named entity recognition. So excuse me, named entity recognition. So we're recognizing entities in the text, names, persons, and stuff like that. So POS is part of speech tagging. So adjectives, verbs, nouns, and stuff like that. Okay, so this is what BERT is good for. Any questions? Okay. So yeah, again, so here's a recap, actually, with much better depiction. So we have the sequence of tokens. So this is sequence of tokens Well, actually, we're putting in a sequence of token IDs because we're basically turning each word or each token from the vocabulary into its index in the vocabulary, as we did yesterday with the characters. We're basically plugging in so the cat set would be, I don't know, something like 1, 1, 2, 2, 3, 4, 8, and 7, 8, 8, 7, the cat set. So these are indices of these words in the vocabulary. We did the same thing for language modeling yesterday for the characters. So this is the same principle. And what's coming out here is are these dense representation, contextualized word embeddings. Okay, so there was this transformer encoder layer, and there were a couple of layers here. And each of them did some very special operations, which we discussed in detail last time. So for each input token, BERT produces contextualized word embeddings. So this is great. So how we pre-train BERT, there were two tasks, if you remember. So pre-training was done not on the downstream task. So we didn't train BERT on sentiment analysis or part of speech tagging. We use something called pre-training and then fine-tuning. So fine-tuning is then when we have the labeled data and do the sentiment classification as usual. But the first one was pre-training on some unlabeled data. Something like pre-training word embeddings. I mean, what does it mean to pre-train word embeddings? You learn word-to-vec on unlabeled data set, just learning these learning the embedding matrix with these positive and negative examples, if you remember, and then you have pre-trained word embeddings. We pre-trained BERT also on some external task, and there were two of them. Do you recall which task we pre-trained BERT on? We're talking about this, so there were two. Okay, so one of them was whether two sequences come after each other in the text or not. It was like the consecutive segment prediction. So we had like one part of Wikipedia and another part of Wikipedia, and either the part of Wikipedia was coming from the same page, which is like the true example, or it was coming randomly from some other page, was like negative example. So it was like this prediction, so binary prediction. Now, I mean, it turned out to be helpful, but not that much. I mean, the most helpful pre-training mode was this masked language modeling. So what was that? We took a sentence and masked or blacked out just one word in the sequence. And the model should learn how to predict back what the missing word, basically. So this was the masked language modeling, right? So again, we masked a word in a sentence in the input, and the model should learn to predict back. Something like language modeling, but not from left to right, but in the middle. So then it answers directly the question, like it's not, so BERT is trained on masked language modeling, but it's not designed to generate text by predicting the next token. Why is that? Why is that? Why cannot we use BERT for generating text as we had before? Because we trained it on like predict the missing word. Can we use it for generating text? Yeah. Yeah, exactly. It was necessarily the next word. It was any word in the middle somewhere, which means we were not only looking to the past, but we were looking also to the future. Yeah, we are looking to the future. So you don't want to build a language model where you need to generate the next token, but you have to look into the future, which doesn't exist yet. So you have to go left to right, and BERT is not going left to right. It's actually bidirectional, which stands for this B, right? Bidirectional. So this the title, bidirectional, and then I don't remember the rest of the title, but it's bidirectional, which goes like left. Well, it's not like left to right. It's both contexts, basically. Okay. So this is the answer. Yeah. So we masked random tokens from the sequence, and well, do the like self-attention over past and future tokens. Okay. So that's the problem. We cannot use BERT for generating language as it is now. I mean, we have to change it somehow, maybe. So how can we use a transformer to generate text? So we would need to predict basically just the next token and not the previous token. I mean, excuse me, just using the previous tokens and predict the next token. What we did yesterday was the same thing. We had a context, the previous tokens, which were characters, and we want to predict a distribution over next tokens. Can we build a transform model that does exactly that? And the answer is, of course, we can do that. And it will perform much better than, I don't know, like character engrams. We had like this narrow language model where stacking basically embeddings together. Or if we use RNN, well, it's also good, but the RNN has to go like state by state, so it's slow and hard to train. So maybe if we use a transformer, but turn it into a true language model for generating next token, we can do like great language modeling, and not only that. So this is going to be our today's content. So what is this? Okay, so this is deep in the BERT model. The heart of those transformer models is this self-attention head. So self-attention, which is taking, so this is some sort of this is a matrix or a list of token embeddings. So if this is a matrix, we can represent it as a matrix, why not? So this is the length of the input, and this is some sort of embedding. I really cannot write B and D. Why is that? It's maybe some, I don't know. Anyway, so this is the dimensionality of the embedding. So we're plugging this in, and what we're doing, so each row here corresponds to one token in the input, okay? So this is still, we're still keeping track which token belongs to which vector, because at the end of the day, what's coming out of BERT is again the same matrix where each word has its own better representation. So in this self-attention head, we did a couple of projections. So we turned this vector, this matrix into a query. So this Q matrix, which might have had different dimensionality here, but still the same number of entries. Okay, so we project it to something maybe smaller, maybe bigger. Who cares? We did the same with the K, and of course the dimension have to match. And these are learned representation, right? I mean, we had these. There were some weights here for this projection, and there were some other weights here for this projection. So they're all learned, which this is what we want. We want to learn good projections. That's the whole thing about deep learning. You want to learn good projections into some other space where you can do, if you have like very kind of nonlinear space, you want to learn projections that once you project all these points, they are linearly separable and you can classify them. That's the whole kind of idea behind. So we learned these projections, and then we had this scale.product, which basically took each vector from the input, from the query, and each vector from the key and made a dot product. And we are filling a square matrix here. So dot product with this, this one with this one would be this dot product. This one with the other row would be this dot product, and stuff like that. So we would basically do dot product with all combinations here, which fills up this matrix of these row associations. Okay, so this was the part of the scale dot product. Well, the scaling was that we divided everything with, I don't know, some constant for a reason, but that's a tiny detail. So we have this scale.product, and then we took for each row, we turn it into a probability distribution. So we take each row and make sure and run softmax basically on top of that. And softmax is doing that. It's exponentiating all the denominator and normalizing by the denominator. So we run softmax. So each of them was basically giving a weight to each particular token, which we then use for weighting the value here. So this is again recap of the self-attention. We've been talking about it for, I guess, for the third time in the lecture, because it's very important concept in the model transformer. So you should really maybe see it from different angles once in a while, and then trying to kind of understand the underlying idea, what's in there. Maybe even like try a few computations. So I would really, yeah, well, okay, maybe just take some matrices like 2 by 2 or 2 by 3 or something like that, and just do computations of self-attention per hand. Just that you understand what's going on. So make a fake, or maybe in NumPy or PyTorch or whatever. Take a matrix, have some W's here. So the projection could be some random matrices, or you make up something so you know how it works. And per hand, it could be like 3 times 3 or 3 times 2. Why not? It could be small. And you created a scaled product, softmax, and the final representation. Okay, maybe do that. Maybe it could be in the exam actually. I remember one exam where we had this. So maybe you want to really try, because it's like a key concept here. I don't want you to compute softmax, on paper, unless it's very easy to compute. But maybe some, maybe the scaled product, or maybe just the algorithm. Okay. So any question regarding attention, self-attention? Okay, I have one. Why is it called self-attention? Do you know where it comes from? Any ideas? Why this is called self-attention? Any crazy ideas? Okay, so I guess that's because the attention is performed on the same input. So the query, and the key, and the value are coming from the very same input. But it's not necessarily the case. I mean, it doesn't have to be like that. It could be that the key query is coming from some, I don't know, some other input, and it should work as well. So basically you can have something which is called cross attention, which we haven't talked about yet, but it was the first paper introducing transformers using cross attention as well. We might do it next lecture. So necessarily doesn't have to be everything the same input into query key and value. It could be different inputs. Why not? I mean, the rest will work as it is, provided that the dimensions of these matrices match. So the length and dimensionality. Okay. So that's why it's self-attention. So we worked so far with BERT, and GPT is using just self-attention, but the original transfer model was using something called cross-attention as well. So it was encoder, decoder. I think we will talk about it like in the next lectures. So it will become clear why it's self-attention. It's much simpler actually. Okay, so let's consider this kind of understood and move on. This was a recap of the self-attention, but I guess it's important. Okay, here's again the actual algorithm, how it's done. So projection of the query, key, and value, and here's the actual computation of that, of the attention. So the scaled score, and here's the softmax. So basically, this is the same algorithm we had last week again. So we discussed that as well. Okay. So this is a recap, because we will change this somehow to make this work for the language modeling task. Let me see. So, okay, this is for the whole input. So the whole X is coming in, right? So what is the X? This is all these, for each row, this is the embedding. So the whole X is coming in, and we can represent it as matrix by matrix multiplication. Under the hood, again, it's if there's a single query, so single row, so E would be, let me come back, E would be some single row, then this is the algorithm doing it for a single row. So not with matrix by matrix multiplication, but a row by matrix multiplication. So we project the row or the embedding to the query vector, and then compute this the weight for each other token. So this is again recap. We talk about it again, but maybe, so this is interesting. I mean, let's spend a second rethinking what is it doing. So again, the E is the input vector, and we have T in number of tokens. So what is it? I mean, the tokens are all the tokens in the sequence. So this is the first token, second. If we have, let's say we have the cat set. And now E is coming from the cat. Okay, so we have the input is cat. Now we're iterating T over T is going to be in 1, 2, and 3 because we're attending to the previous token, to itself, and to the future tokens. We're iterating over all tokens in our sequence, okay? Why? Well, because we're computing basically, we're computing the dot products between all pairs of vectors. So from the future, from the past. Okay? So this is, we're projecting the key, and then this is this first, the dot product, then the softmax, and this is giving me the value, the alpha. So for each token, I'm getting one of those alpha. So the D will have some alpha, cat will have some alpha, and set will have some alpha. And then I will weight these, use these alphas to weight the value which I'm producing out. Okay? Any questions? Is it really clear, or you have some doubts about it? So the key point here to remember is that we're looking at all tokens. So we're looking also into the future to learn how the token is relevant to my actual token. So if my token is cat, I'm looking how D is somehow relevant for me at this position, how cat is somehow again relevant to this position, and how the next token set is relevant to my position. So I'm looking on the whole context from left to right. So I'm looking into the future, right? This is looking into the future. I'm iterating over all tokens. That's why in each word, in each token representation, I have ingested here, I have ingested information from all the tokens before and after. This is where it's happening. I'm taking weight for each token from the past, current token, and from the future, and I'm saying which one of them is more important to take into account to create this new representation of this current token. Okay? Does it make sense? Which breaks the causality in a way. Like, I'm looking into the future to see how my representation should be important for this current token. So yeah, I'm looking into the future, which is good as in BERT for, if you want to like learn representation of the whole sentence, this is good, or classification or tagging, this is great. But for predicting the token, so using this language model where we are looking into the future, we can't do that. So we have to change this part somehow, okay? And what we'll do is very, I would say, like tiny little adjustment, which will turn this thing into a causal language model. So the core is here in this algorithm, this scale attention, in this self-attention, how things are attending to each other. That's why I said it's maybe important that you try to use this with a tiny little detail. So there's the 3 matrices, 3 vectors, or even that with a single vector. You try per hand kind of see what's coming in, what's coming out, and why is it actually attending to the other vectors, okay? We might do it actually in the exercise if you want. Let me know, okay? we can try it. Why not? Excuse me. So we need to change something here because we don't want to look into the future. We want to just look into the past. So we need to do something. Again, actually, I have an example here. Okay, so yeah, sorry, I can't see in the to the future here as well because I'm using this external where I don't see like the next slide because the other software I've been using doesn't work on Mac that nicely. So excuse me, I do have an example. So this is the example of single query unmask attention. Okay, so here what do we have? We are at position 2. Oh, it is the same thing. So we are at position, well, here, cat. And we have 3 tokens. This is great. So it's exactly matching what I was talking before about. So our query, we did some projections. So we have already the query. Okay, so we have the query vector. And it's just a small dimension, just a 2-dimensional query vector. Okay, why not? This is the query vector, and we have keys, 3 vectors. So this is a key for the first token, for the second token, and for the third token. Why is the key different? The key to K2, why is it different from the query? Why these values are different? Because it's the same token? Well, because they're using different projections, right? I mean, if you look back, the key is created by projecting through this WK, and the query is projected by WQ. So these are different vectors, okay? So, but again, if we have the cat set, so this would be the key for this would be a key for cat, this would be a key for set, and this is a query for the second token, which is cat. Okay, everybody's with me? Awesome. So let's create a matrix, from these k vectors. So stack them together. So we would stack them together and transpose, which means this is the first row now, second row, and third row. Okay, so we just stitch them together and transpose just to match the multiplications. And now let's do the dot products, okay? Because we're multiplying this. Okay, coming back to the algorithm, we're multiplying here. We're multiplying the query with each of these keys of each of the token. So let's do it. So our Q was 11, 12. So we make a dot product with the first key, which gives us some number, 35. We take the query and multiply, or make a dot product, dot product with the second key, so second word, and again, this is dot product basically, and the same for the dot product. So we have the raw associations. Does it make sense? Okay, it's multiplying or making dot product of two vectors. Okay, so we end up with the raw scores for this at position 2. We have these raw scores: 35, 104, 170, 73. So where the raw scores are again, let me just come back to this. These would be the raw scores here. Okay, so this is the dot product of the second query vector here, second query vector with all the key vectors. Okay, so this would be our row here. And then the next thing is, so after these raw scores, I'm gonna turn them. Well, I'm ignoring scaling here just for sake of clarity or simpleness. So simplicity. How do you turn this into softmax? Well, you know how to turn a vector into softmax. Like it's gonna be exponentiation of the number divided by the sum of exponentiation all the sum. Well, okay. So if you turn these numbers into softmax, what's gonna happen is that, well, in the linear scale, these are not really different numbers, like 35, 100, 170 looks linear. But of course, if you push them through softmax, the winner takes all, right? So this number is so big that basically it will take all the mass. So it will be like almost 1 probability. If you do it really in PyTorch, you will get 1. So this is how softmax works. I mean, softmax basically a winner takes all. If these numbers were almost equal, then you have some sort of little bit uniform probability distribution out of that. But if you have something which is a higher value than the others, it will take everything, and just the other will be completely almost 0. So try it in Python. I mean, it's interesting. I thought like it's gonna be like, well, maybe 10%, 20%, and 70%, but not at all because of the exponentiation. Like, exponent makes the difference. So this is the alpha values, which means then I'm gonna, do I have a value here? I don't have a value vector, but basically I'm gonna multiply the value vector, each position in the value vector by this corresponding alpha, which means this is where the most value will be put, but this is a token from the future. This is the third token. We are at position 2, but look, all the attention should be put on the next token at position 3. Yeah, which kind of it's cheating. It's looking into the future, and it's really breaking the causality in a left to right language. Okay, so this is how the basic single unmasked. So why is it unmasked will be clear in the next 2 slides. This is how it works. And it could be, in this case, it's actually using the information from the future to make better representation of the current token. So this is actually one example how this could turn out to be. Made up numbers, but why not? I mean, that's an example. So any questions? Is it clear, like, why is it basically leaking data from the future through this weights? Okay? All clear? Okay, good. So that's bad. We don't want this. We want something else. We want to attend only to previous tokens. This is the key. So if we have 4 tokens, well, if we are at position 1, let me just make an example. Cutest cat set. Okay, we have 4 words. And at position 1, okay, this is let's start with position 2. It's maybe more, let's say, convenient. So we should at position, oh no, let's start with 1. At position 1, we should not be looking into the future, right? So if we are here, we shouldn't be looking at the next words. We can't do that, right? We shouldn't do it. Okay, so if we are then, let me change colors because I can. If we are at position 2, can you see that? Okay, cool. If we are at position 2, well, we can look back if we want, that's fine, but we shouldn't really be looking into the future. We cannot attend to the next tokens. Yes? Here, that's absolutely correct. Thank you. How do you turn 3 into 4? Like that. Okay. Sorry. Can you open a GitHub issue? Somebody. I mean, somebody did last time was really cool, so I fixed that. Please, please, please. Thank you very much. Much appreciated. Because if I write fix me, I forget it. If somebody just opens a GitHub issue, I'll fix it in a second after we finish the lecture. Okay, so this is 3 and 4. Thanks a lot. So we shouldn't be attending to 3 and 4. Then here at position 3, we are here. So we shouldn't be attending to position 4, but we might look into past. And obviously at position 4, we can just look in all of them. So now you see a little bit of pattern here emerging, right? So you see you cannot look into the future, but you can look into the past. So if these were our raw associations, what we are doing with these raw associations again? Let me come back to my beautiful blue. Okay, so what are we doing with these associations again? So we turn each of them, we run softmax. And we turn it into 1, 2, 3, 4 some probability distributions. So like this and this and this, right? This is what we're doing. Softmax on each row of this row associations. It was in this, just coming back. Here we had an example. So we took this row and run softmax and go to probability distribution. And you would do it for each row, basically, excuse me, here. For each row association score, you would run the softmax on each row. So this is it. We're running this on each row. So what we really want here is we want to assign 0 probability to the future tokens because, I mean, 0 weight. We don't want to wait in future tokens. So for example, if we are at position, let's say in the second position. So in the second position, what was that? We can look back. Okay, 1, 2, 3, 4. At the second position, we want to add 0 value to the future tokens. So we don't want to weigh them in. We don't want to just kind of delete this value from the future, which we do by basically zeroing out the result of the softmax. Why? Because then if you multiply, then if the future tokens have 0 value, excuse me, the 0 weight, if this is 0, well, then the resulting value will be also 0. So the value from the future will not, excuse me, the value will not be affected by the future tokens. Does it make sense? We want this, like why this 0 has to be here. So what we want here is that something like that. This output, and for the third token, we want this, and for the last, something else. So we want to put 0 value on the future tokens, which now Comes to the question, well, it still has to be probability distribution. So what does it mean? How can we fix it? How can we make this work in a probability distribution? So what do we need to do? So we need basically to compute a softmax only on the current and preceding tokens, right? So this is softmax to have the probability distribution here. So and now it will be somehow. So this has to sum up to 1, right? Because I'm basically saying, well, I'm ignoring the future tokens and I'm just spreading the probability distribution. I'm spreading the weights over the tokens I can attend to, like the previous ones. Okay? Any questions? So it's basically saying this doesn't exist. And here, run the softmax for the first one, run the softmax for these 2, run the softmax for the 3, and run the softmax for the 4. If we do this, we're turning our attention into a causal attention because we don't look into the future anymore. We're just using the past tokens, which is what we want. We are not cheating. We're not looking into the future. There is no information from the future coming into the current token because we're ignoring basically the future tokens here. Okay? Very cool. So how can we do that? How can we do that? Thanks for that if you just open the issue. So how can we do that? We have this algorithm. So can we plug it in somehow? Well, maybe we can. Let me just try like what could be like the simple solution, how to fix that? How to implement this thing, like softmax on, well, different softmaxes on different sizes. So, well, there is, okay, so again, we want to attend only to previous tokens. So we actually we want to ignore the future tokens. So here's a snippet of the algorithm of the self-attention for a single row. So again, what we're doing here. So what we are doing before is to take a dot product of the query with each key. But now, okay, let's run this. Okay, let me just come back to the algorithm, right? We are saying, okay, for each normalize it using all the dot products. So run it for all the tokens. Now I'm saying, well, maybe run it only until the current token. So it would say, well, the sum, for example, here, I'm not normalizing by the whole, but just by those 2. And here I'm exponentiating. So this is basically running softmax on a subset. So if t is 2, for example, if t is 2, this is running softmax only the first 2 tokens. Okay. So this is what I'm doing. And well, maybe, okay, let me see. This is maybe wrong. Maybe this should be just for t, maybe for, no, this is true. Well, okay, doesn't matter. This is actually, I mean, and then I say, okay, for the rest tokens, let's just zero out. So this will be 0 and this will be 0, something like that. So this is like a naive solution, which maybe it's even like wrong. I don't know. I didn't check. I was like, the first idea, if you want to run softmax here on 1, here on 2, here on 3, here on 4, you just kind of change the softmax to run on a subset of these tokens. That's the idea. And the rest will be just zeroed out, like naively here, a for loop or something like that. Maybe it won't work even, but it should, like theoretically. Maybe I made a mistake here. But the idea is like you can do that. I mean, you can use a for loop and basically kind of extend the range of softmax. So here it would run for the first token only, for the second, for the third 3, and here on the 4. So you will have different softmaxes and the rest will be zero out. This is the idea. Well, for loops are bad, so we should vectorize this operation, okay? We should make it somehow, so we're coming to the heart of everything in deep learning and everything in deep learning with NLP, which is make it vectorized make it broadcastable. Like broadcasting is a thing because you can parallelize it easily. I mean, if you can vectorize it, it will run like 100 times faster than for loop. Anything you do, like matrix, if you can turn it into matrix multiplications, it will work on a scale. If there's a for loop or something like sequential, you will have issues, which means it will train maybe in a month instead of 1 day, something like that. Maybe not, but this is when you really try to vectorize all these operations so you can parallelize them. So how to vectorize this operation? Well, we will make a little trick here. So these are the raw associations, right? This is what's coming into the softmax. So I'm gonna run again. Here I wanna run softmax on the first row, on the second row, but I just wanna somehow get rid of those and turn them into 0. So I will replace all these things that I want to ignore, so to say, by minus infinity. Minus infinity, it's not a number, obviously, it's a concept. But here, yeah, you might be thinking like, why minus infinity? Like, why? Well, okay, let's have a look. What is the softmax? Let's compute the softmax of this row, okay? So what's the formula of softmax? We had it here. So we have softmax of this, let's say, softmax of 11 in this row is, what was that? Exp11 over exp11 plus exp minus infinity plus exp minus, this is infinity plus exp minus infinity. Okay, cool. Oh, what is exp of minus infinity? 0. That's it. In a limit. In a limit. I mean, you don't want to work at infinities anywhere on computer. Although if you plug in definitely in Torch, maybe even NumPy, if you plug like NP infinity or minus NP infinity or Torch infinity, it won't break. So you can compute exponential. I think you can do that, like exp of minus infinity will give you 0 because it's like an exception, so it will just, it won't try to compute like the real value of infinity, but it knows by a limit infinity of exponential of x function. Why is it so, right? I mean, here's 1, and this is the x function, which means it goes to infinity. It goes to 0 at minus infinity. This is cool. So we're turning those into 0. Okay, nice. So then what will be the next one here? The second soft max of minus infinity. Well, even just by the numerator, it's gonna be 0. Okay. So plugging in this minus infinity is basically zeroing out the output of softmax, which is exactly what we want. So exactly this, the output will be the same number. So some number, something. Well, actually, it will be 1. Why this will be 1 after softmax? This will be 1, 0, 0, 0. Why? Exactly, yeah, exactly. So this is like all the mass is here. Well, here in the second row, it might be something like 0.4 and 0.6, or maybe not. It's maybe 0.3 or 0.7 because I'm distributing the probability to 21 or 22, but exponentiated. So there will be some. Maybe it will be even bigger difference. Anyway, so some numbers, and 0, and some numbers. That's it. So, okay, minus infinity is cool. So basically you replace the next tokens if you're at position 1. So everything from position 2 and upward, you just replace by minus infinity. And then you just run the softmax as before. Just no for loops, nothing like that. Just for all of them, you just run softmax, and it will give you what you want, like this sort of kind of zeroing out the future. Okay. So any questions? Okay. How exactly you put in, you do this? It's called masking. Unidirectional masking for self-attention. Masking means you put some binary mask, and unidirectional means it's left to right. That's the masking. That's why we were talking about unmasked self-attention, because there was no mask, but we were putting a mask. And the mask is very simple. So the max for two positions, so well, T, Z, and Tx are just in the length of the input. So like 1 to length of the input, which would be, I don't know, like we have 4 tokens here. So, and it's saying, well, okay, put me just 1 for those which are allowed to, and put 0 for those from the future which I don't want to take into account, right? I mean, this is the mask we want to have. Like we will use this mask for plugging here the minus infinities, or keeping the value. And we can create it basically by this, just a simple decision. Like, yeah, if the index is the same or lower, so I can attend to it, I put 1 here. So for example, here at position 2, so Tx is 2, Tz is 1, so I can put 1. Tx is 2, Tz is 2, I put 1. Tx is 2, Tz is 3, okay, no, 0. So this is how I create a mask. Creating the mask, this thing is super easy in PyTorch. It's just, I think there's even a function called trail, like a lower triangle of a matrix. I mean, it's very easy, you know, or even like just using this binary predicate. So you can very easily create a mask. It costs you nothing. It's just a single operation, something like that. So it's not very hard to create a mask. And what you want to do is then to index your index your tensor. So what, you know, if you have this mask, then you want to use it for. So let's say we have 4 numbers, 1, 2, 3, 4, 5, 6, and so on. And you want to put this mask somehow, like saying, okay, for this mask, everything which is 1 remains. So I'm going to paste it here, and everything which is 0 will be minus infinity. I mean, this is like 2 lines of operation in PyTorch. It's parallelized, and it's just it's a way of, you know, like indexing vectors or indexing tensors in PyTorch is super fast, super easy. And creating the mask is very easy. So this is like how you get rid of all those kind of for loops and stuff like that. So you just basically masking vector and replacing with these with minus infinity. Once you do that, once you have these minus infinities in there, you just run the very standard self-attention. So, okay, here's again the algorithm. So I'm projecting query, keys, and values. I'm doing the Ross association. So this is known. This is a standard thing we had before. And here's basically masking the plugging the infinity, saying, well, if in the mask, so this means, what does this thing could mean? Yeah. Yeah. Exactly. This is saying like negation. So if not mask at this position, which is like, well, if mask at this position is 0, then plug in the minus infinity. So this is a for loop, like for algorithmic reason, but you won't implement it like that. You will use this tensor. You create a mask and then basically indexing the tensor and using some built-in PyTorch functionality to do it fast, not with a for loop, indexing and slicing and stuff like that. Okay. But basically it's saying, well, okay, just plug me these minus infinities. And this is again odd. I mean, we had it before. Done. So the only trick to turn like bidirectional self-attention into causal self-attention is using masking. And the masking is saying, don't look into the future, just look into the past. By doing that, all tokens can only, so because, okay, maybe we have, okay, here's again, okay, any questions here so far? Is it clear, more or less? Which means, so this was like before we had no masking here, so we had query key, scale.product, softmax, and stuff like that. we just plug masking here in between and turn it into mask self-attention. And this is how we turn it from the BERT encoder into GPT decoder. So like this is the name of these models, so decoder and encoder. But the main difference is just the causal masking here. And it's saying, well, after, okay, if I have a input d cat set, which I turn into, it's gonna be a vector, cat, it's gonna be a vector, and set is gonna be a vector, which is my x. So this is equal x. And I unplug it through this self-attention. Well, I get again x, which will be the first vector, second token vector, and third token vector. But the first token vector will only have kind of ingested information from itself. The second vector will only ingest information from itself and the previous token. And the set, the last token, will ingest all the information. But none of them will look into the future. This is what I'm preventing by this masking. So I learn contextual representation of each token. Again, I'm getting embedding in, embedding out. But these embedding know only about the past, not the future. So this is basically what I need for language modeling. I want to kind of condition on the previous tokens, do something with the next token. And this is how we achieve it here with masking. Okay? All right. So here's again in words. So the output from 1 to t of this, so this is the output matrix, only depends on the 1 to t. So it can be used to predict the next thing, maybe the next token. Okay, so this is it. Let me just see what's here. Okay, so let's finish this and then have a break. Okay. Okay, so let's plug it into the transform model. So now it's the GPT sort of decoding all the transformer, and this is how if you get an input, how it goes through this model and generate what you want. So the input, again, for this model this is the same as in BERT, is a sequence of token IDs, right? A cat set, ID1, ID2, ID3. This is the same. So input is a sequence of token IDs and some trainable parameters, all these weights, all these matrices in the for all layers, multi-head and stuff like that. And the output of this decoder transformer is a matrix of okay, Lx. So Lx is the length of the input. So if we have, I don't know, if Lx is 4, then the output will be what? The output will be a matrix. Okay, so this is going to be Lx. And what is this? And NV. What could that be? Any ideas? Yeah. This is the size of the vocabulary. Exactly. This is the size of the vocabulary. So we've been using also this, but also NV. These are the same things. Size of the vocabulary. And each of them will be, oh, each row is a distribution over the vocabulary condition on the previous tokens. Okay, so we will have here a probability distribution. So each row will sum up to 1. So if we have 4, then we will have four rows. So 1 row sum up to 1, row for the second token, sum up to 1, third token, sum up to 1, and the fourth token sums up to 1. Aha. And each of them is a conditional probability of this row given all the previous rows, all the previous tokens. Oh, this is great. So for example, if we have the cute cat, let's say a cute cat set, Then, for example, for the cat, if we are, no, not a cat. If we have position 1, 2, 3, we would have here 1, 2, 3, we would have here a probability distribution over the vocabulary given, so P X, excuse me, let me just be clear. Probability of token at 3 equals some word from the vocabulary, given that T1 was A and T2 was Q'd. This is a language model. This is a language model. We can look at the probability distribution here and say, well, what is the most likely word to happen? And if it happened to be a cat or something from the probability distribution, I will just predict it and generate the next word, cat. Okay, I move to position 4. So again, I'll get here. So here I'm position 4. And at this position 4, I have a probability of a word T4 given T1 is A, T2 is Q'd, and T4, we generated cat. Okay, so cat. Oh, this is a language model. I can generate the next word until I run out of memory. You know, until the LX, which is a hyperparameter of the model, like 500, 1000, and it's a hyperparameter of the model. There is some maximum length, but it's basically a language model. It gives me at each row probability distribution conditioned on the previous ones. How I achieve that? Well, by using this masking thing. Because I'm really, trying to predict the next word. I train it on language modeling, as we will talk later on. So it's trained on basically predicting the next token, as we did yesterday. I mean, we are having like previous tokens, previous characters, and try to predict the next character. And this is how we learn all the parameters of the model. We're gonna do the same thing here because this is what's coming out. I mean, this is a conditional probability distribution. Conditional probability distribution of that given the previous ones. This is it. This is how I turn my transformer into a language model by causal masking. Okay? Any questions? So can I use it for generate text? Absolutely. Yes. I can sample from these probability distributions or take the most likely prediction and then just get the next word. So if you remember the same for BERT, which we had at the beginning of the lecture, this is the same, almost, like pretty much the same. So we have this input of the token IDs. We have the input embeddings, which is the embeddings for the word piece, and the positional embeddings, as in BERT, the same thing. So we need to keep track of the positions. Then we have this transformer layers, which are now decoder layers because there's this causal masking in here, L layers, and then there's a final layer, which is just turn the matrix into probability distribution. So it's basically running some softmax on top of that. And that's it. That's the only difference we'll hear. I mean, the only difference was actually only in one attention head with this masking. The rest is just a transformer architecture as we had for BERT and encoder. Okay? So zooming in, just to make sure that we're, transformer decoder layer. So the layer has multiple heads. So there's a head 1, head 2 until head, I don't know, 24, until you run out of memory. So this is parallel heads, and they're just somehow taken together and returned back. Okay, so this was like each transformer decoder layer, multiple heads, and each head. Oh, okay, we had this head already in the BERT, but now in GPT, there is just a, oh, excuse me, I messed it up. No. That's not true. Because there is some more operations than just the parallel heads. Okay, let me just delete it. So the decoder layer looks like that. We had this multi-head self-attention. Now it's masked. And we had some, what was this again? Linear, Galois, and linear. It has a name. Yes. It's a multi-layer perceptron or a feed-forward network. So we had a feed-forward network. We had this multi-head attention. And we have this layer normalization as well to make sure that each row basically is normalized around, is centered around 0 and has some standard deviation to 1, something like that. So we are basically rescaling and shifting all the values. We invert, so we basically move this layer normalization before. It used to be after the sum, but in GPT they just move it before. That's the only change they did. So why? Maybe empirical evidence, maybe, I don't know, maybe there's some theoretical foundations for that. Who knows? I didn't find any in the papers. There's nothing like why they did that. Anyway, so this is the same as we had before, and also we had these residual connections as before as in BERT. So going one direct way and going the self-attention here and just summing them up. So this is the same thing as we had before, just we moved the layers before. Okay, so now only the multi-head self-attention, now it's changed because it's masked. And as we know, the mask we talked about before. I mean, each head is this one, and the only thing we edit is this mask here. So this is the only difference to BERT. Architecturally, I mean, it's pretty much the same. So layers, each of them consists of these MLP and multi-head self-attention and normalization. Their ordering is a little bit changed for some reasons, but pretty much the same. Yes? Mm-hmm.
This is happening in every layer.
Yes. Yes. And this is happening in every layer.
The tension of few layers earlier is always happening in that way.
Yes. This is happening in there's multiple heads in parallel, and each head looks like that. Okay. And here's, I mean, if you can compare it with the algorithm of BERT, this is now the same thing in words only. So we change the normalization. It's now first. We have the multi-head attention. Now we added masking, and that's it. That's the only change in the code. Like once you implement the masking in self-attention, you just use the same kind of higher level architectural blocks to put it together. I might have some. Let me see. Let me see. So I need to stop sharing and share something else. So, okay, so this is, if you come here, let me just maybe share this on Zoom as well so everybody can see that. So here's actually a pretty beautiful visualization of GPT. It's called Nano GPT because it's small. So, okay, here's Nano GPT. And if you zoom in here, so you can basically play it from the very beginning. So from the embedding layer, let me just make it bigger. Embedding layer, then there's layer normalization, self-attention, and you can basically here zoom in and move it. It's like 3D. It's pretty cool. It's actually very, very cool. Okay, so it goes through all these parts, and there's some explanation to each of them, and you see like how big this thing is in parallel, what actually is being done in these multiple heads, and how this actually each value is computed. So I guess you can really go into each value here. Okay, layer normalization. Okay, you see Q vectors, key vectors, their weights, and just once you start exploring this, make sure that you know whether the input are row vectors, as we have in the lectures, or column vectors. I guess this is using column vectors, which means things will be transposed, and don't be surprised. Like many things will be transposed, so softmax won't be running on a row basis, but maybe on a column basis. Okay, but everything is pretty much the same. I mean, it's just a design choice if you do like row vectors or column vectors, and you have to adjust everything accordingly. So this is Nano GPT. You see here's they have like 4 transformer layers, I guess, or even 3. 1 transformer layer, 2nd transformer layer, and 3rd transformer layer. And then there is this, oh, come on, this is actually pretty cool. And there is this, oops, I cannot navigate it. I mean, I'll post it on Discord so you can see. And you see like then the final softmax and prediction of the next word. So, okay, just to show you the context. So this is small GPT-2. So this is the Nano GPT, right? 3 transformer layers. This is GPT-2, a small one, because the large one had like 24 transformer layers. So this is only 12, I guess. So even more parameters, like 1.5 billion parameters. And I mean, you can really zoom in and see like how I cannot zoom in with the touchpad here, sorry. So this is the size of GPT-2. This is the large GPT. Okay, so multiple things at once, or maybe parallel models. And just you see the scale of GPT-3. Okay, so I mean, it gives like things in a proper ratio, like how large these things are, how many parameters, and how many models are there. I mean, about GPT-3, I mean, this is, I guess, some assumptions because we don't really know all the details of GPT-3, but we do know more. We do know details of GPT-2, small and large. And Nano GPT is something which Andrei Karpaty built in there in a series of YouTube tutorials, very cool ones. So let me just stop here and come back to the lecture. So this answers your question, like, is it, where are we? Like it's combined all these blocks. All of them have different weights and different weights or parameters, so to say. So each of these blocks, each of these predictions for each layer will have its own parameters, which will be the key, query, and value projections, and they have to be learned. So if you add more transformer layer, you will have more parameters. If you have more parallel attention heads, you will end up with more parameters. If you add a length of the context, like the input, you will have more parameters because all the matrices will just grow. So that's why I guess BERT had an input for, well, BERT is not a decoder, but I guess GPT-1 had maybe 512 tokens input, and GPT-2 had like 1024, like double size, because they just had a much bigger, computer to run this. So this is it. Like you just grow bigger. We'll come to that later, but this is just to show the architecture. So the difference between the BERT forward passes we discussed, we switched the ordering of layer normalization. So line 6 and 8. So we put them before the attention and before the feed forward. There is no final layer projection. Okay, well, in a way. And the attention is now with left to right masking. That's it. That's how we have the decoder GPT. So any questions so far? Okay, let's make a short break. Let's make the standard 7 minutes. And then we'll continue. Oh, come on. So what is remaining? So we talk about the architecture. We talk about the differences of the encoder with the decoder and said like, well, we can use this for language modeling. So the main thing remains, well, we know the architecture, but how do you conceptualize this training? So is there like pre-training and fine-tuning? What is there? How do we train this thing? So we should talk about it. Actually, if you recall the training of the encoder, where we used, okay, so in the encoder in BERT, we were masking words which we want to predict. So there was this kind of a mask word token, and an extra few steps in the algorithm. Well, now for the decoder training, it's much simpler. There is no such a masking of missing words. We're using the masking, the causal masking in the attention itself, so it's not an extra step, as we saw. So what we're running is if we have a bunch of training data, so these are sequences of data, let's say, I don't know, Wikipedia articles or some book articles. I guess for GPT they used books, and then later on they used the whole internet. So we'll talk about it later. So some sequences of text. We have some number of epochs which we train the model. What is this? Yes. The learning rate. Yes, the learning rate. So this is a standard training by SGD, stochastic gradient descent. You might do it typically with some better techniques for training, for example, Adam. And I guess we might spend some time on Adam later on, like in the remaining stuff for deep learning and NLP could be Adam, but this is standard SGD. So what we're doing here is iterating over the training data and then run the inference. Well, run the forward pass on the transformer, which gives us this matrix of probabilities, these conditional probabilities, as we had in 3 slides back. So we run this on the transformer, and we compute the loss. And okay, this is interesting. So this is some sort of negative log likelihood, which is a fancy name for some sort of categorical cross entropy. Exactly, this is actually categorical cross entropy. And then we take the loss, take the gradient of the loss and update the parameters according to this gradient and the learning rate. So this is standard SGD stuff. The only thing might be, okay, what exactly is going on here? So let's have a look, in the how exactly we compute this negative log likelihood. What really means these indices here in this matrix. We did this for the BERT model. We do it now for this decoder as well to really understand how it's computed. So, okay, let's have a input sequence, the cat set again, which is these are. So what are those? What is it again? These numbers. What is it again? Just set it to check. What's coming into the model? Yeah.
Token indices.
Yeah. Token indices. Indices. So, and we plug it into this decoder transformer, and what's coming out here again? Okay, so this corresponds to the first token. This corresponds to the second token, and this is the third token. And we're predicting those into probability distribution over vocabulary. Okay, so this is the output of the decoder. So this row sums up to 1, this row sums up to 1, and this row sums up to 1. So this is what's coming in, what's coming out. We talked about it, 10 minutes back. Okay, so this is what's coming in. We have the P. We can ignore the theta, actually, it doesn't matter. So this is just a P matrix. Okay. So now let's take position number 1. So we're at position number 1. Why position number 1? The cat should be 2. Excuse me, should be 2. Because we have the cat. So no, next word. That's correct. Yeah. Yeah. All errors are +1. Anyway, so here, this model at position 1 should predict the next word, and the next word is cat. Okay, so we're at position 1. We should predict the next word. It's cat. So here we have a probability distribution, and at position of index cat is some number. Okay, so this is it. So our gold label, so to say, is the true word, which is cat, which is this one-hot encoding with 1 at the position of a cat in the vocabulary. Okay, makes sense? This is one-hot encoding of cat. Clear? Okay, 0s and 1 at position where it is. And here, this is the first row of the matrix. Some numbers sums up to 1, some numbers, and we have some numbers at the position 11987. Okay, so there's some number. So let's have a look at categorical cross entropy loss, where we go through all the elements of these vectors and multiply the gold value with the logarithm of the prediction. So let's plug in the values we have. So, well, actually, for all case except of position 11987, the sum will be 0. Why? Because we have all the zeros in the gold label. So we only matters the one at this position. So that's why we plug in here 1, because, well, this is 1 at position 11987. And there is the lookup here is what is it going on at the position 11987 at the predictions. So what's actually doing these predictions, we're taking the first row. So we're taking the first row and this value matters. So this is indexing again. And what it actually means, 11987 is the t plus index, it's t plus 1 index in the input sequence. So basically I can express this as the 1, which is my t, so my position 1, and this is the next token, so plus 1. And now I'm finishing by changing 1 into as t, so this is how I get the final expression. So I'm taking the current token row in this matrix and look into the index here, the index which corresponds to the next token in the sequence. Okay? So this is one example, and basically this This explains exactly what I'm doing here. So I'm doing it for all the tokens in my sequence. Okay, so I'm computing the log likelihood for all the tokens in my sequence. I'm summing them up. So basically, I'm running sort of multiple models at once or multiple losses at once, because for the first token, I'm running loss like how to predict token 2. At position 2, I'm running how to predict position token 3 up until the length of the input. So I have for each of these positions, I'm computing the loss, how it predicts the next token in the sequence. Okay, so at once. So it's learning basically multiple things at once, well, basically all the length of the input. It's learning, well, if I see the first token, how can I predict the next token? If I see 2 tokens, how can I predict the third token? If I see 3 tokens, how can I predict the fourth token? And so on, so on, so on. And because it's autoregressive, it's always looking into the next word in the sequence. I mean, I have the gold signal from there. So it's autoregressive means it's eating up itself in a way, or self-supervised, basically using the next token as a signal for for error prediction, or excuse me, for prediction and computing the loss on the error. Okay? Good. So this was the training. That's it. Very simple. No next sequence prediction, it's gone. Mask token thing, not at all. We changed the prediction into basically language modeling. Predict the next token given the previous tokens. Very simple, simplified thing. The only change is in the architecture is the masking. That's the biggest difference. Now decoding. Okay, so I have the model. I want to maybe sample from the model something like we generated names, so we can use it for genetic names as well if we have the tokens word characters. These are subword units mostly. With one difference, so we condition on something which we call the prompt. So we have the model and we put some sequence of tokens, which we call the prompt. And what we want is some sort of continuation. So again, sequence of tokens, which kind of continue the prompt. And you know this from prompting GPT. This is exactly what you're doing. You type in the prompt. There is some prompt behind the scenes already, which you don't see, basically. So there is some long prompt saying like, okay, you are OpenAI model ChatGPT, you're a nice guy and just behave nicely and blah, 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 and answer all these users' questions and stuff like that. So this is part of the prompt. You finish your prompt, it's saying, okay, what will be in the exam for deep learning for NLP? And This is your prompt, and then it will spit out some, given, whatever, I don't know, like you put some prompt, and then it starts spitting out the rest. And it's how it's spitting the rest, it's generating token by token. So how it works really? Well, okay, here we're running this for loop as a, for all indices before you reach the length of the generation, but you might have like stopping criteria, like end of sequence token or something like that. So this is one simplified way of looking at this. And what you do is, well, you take your input, your prompt, your existing prompt so far. It will change later, but now you have the prompt. You run it through the decoder transformer, which gives you the probability distribution matrix. And what you select is the what is that? Well, basically the last token's probability distribution, which predicts the next token to be generated. Right? I guess this is the last row in the matrix, and always, what matters is plus minus one. You want to make sure you take the last row in the matrix because you want to generate the next token. So this is the probability distribution of the last row. So this is the row from the matrix. I mean, right? We have this matrix here. So this would be the last row of the matrix, and you want to use it for generating the next token in a sequence because this is how the model was trained on. So you have this probability distribution, so it sums up to 1. And now you sample from this probability distribution a token. So how are you going to do it? I mean, there's one where, what is this? Okay, so let's have a look. So first, what is this tau? So the tau is a parameter called temperature, which is shifting a little bit, where it's changing the distribution of this. So it's changing a little bit of distribution. So if you, it's rescaling your distribution. So if the temperature is, I don't know, let's have an example. I think we had an example of temperature somewhere, but maybe you should recap that. So let's say we have a probability distribution like this. And if you want to rescale it with temperature, so if your temperature is high, it means all the values will become sort of lower, which means more uniform. So this is low temperature. Excuse me, high temperature. Right? You're making each number of that to power 1 over some high number, so it's making it smaller. So everything will be smaller. And if you normalize it, you will end up with some like more uniform probability distribution. If your temperature is low temperature, the highest value, I mean, everything will be multiplied by some number, so it will basically grow. But then after normalizing, your high value will become even higher, so it will be more spiked. So this is it. Okay, so you're basically by this temperature, you're saying, well, how much more uniform are you going to be sampling from, or how less uniform are you going sampling? It's you're using it for more, let's say, more variance in the generated thing. So if you are always going to sample the most likely thing, the models will become maybe more repetitive or just not really exploring the space. While if you say, well, okay, I can sample with more probability from the unlikely things, which means a high temperature, it will be more random in a way because you're shifting the weights in your probability distribution. So this is temperature parameter. I guess in some, I mean, not in GPT, but if you use some inference models in Hugging Face, you can run basically prompting of some models. And I guess there's a parameter for temperature as well. So you can set up temperature in there and you get more randomness with high temperatures. And if your temperature is like very high, your probability distribution of the next token is just completely uniform, almost uniform, which means like whatever comes out will be completely random, almost random. So like very incoherent bad text, so to say. Okay, so this is the temperature parameter. This symbol.
Say proportional to, but I don't think that's listed.
It's exactly what is it? Proportional to. So this is a probability distribution. If you change it, like multiply or make it smaller, make it bigger, you need to renormalize it to make it probability distribution. So if you just would do the sum, if you normalize it, you get a probability distribution. This means like, well, it's proportional to. So it's not a real probability distribution, but you might want to make it probability distribution by renormalizing. So the only thing is like if you don't do any temperature setup, if temperature is 1, then nothing will change, and you're just sampling from the actual output of this matrix of the decoder. But you can change a little bit, shift the uniformness or non-uniformness by adding this temperature. So once you sample the next token, so this is the next token is just ID of that ID of the token. You add it to your prompt by just concatenating token and run again. So basically token, next token generated, next token generated, next token generated, next token generated. This is it. This is how it works. Basically token by token generation. Okay. And what you return is basically the generated output. So there is some indexing here. So always make sure, that you output not the prompt, but what's generated afterwards. But the whole idea is generating the next token by getting probability distribution from the old period. So basically language modeling, seeing all the context, what's the probability distribution over the next token, over the vocabulary or the collection of subword units to generate the next one. And you sample randomly. You can take the maximum one, or you just basically really sample from a distribution, and you can change the distribution by being more spiked or being more uniform by this temperature. Any questions? Okay. This is it. This is GPT. You can build it if you have enough resources and enough data. So how it happened to come to, so just a few words about the evolution of GPT. So at the beginning was this transformer encoder decoder. So the paper was called "Attention is All You Need," and this was really a breakthrough paper. So people from Google, 2017, and they proposed encoder, which we know from BERT, so encoding a sequence, and the decoder, which we just discussed today, and the model was kind of combine both things together with something called cross attention. We might spend some time on that in the future, but what we followed was first looking at the encoder as a BERT model, and then today looking at the just decoder model as GPT, but originally came from this encoder-decoder transform model. So, and it was a huge success in machine translation, and it was adapted by other people, and later on also, I guess these people were also from Google, use it for summarization, text summarization tasks. So they took this original model, but dropped the encoder and used only the decoder, as we talk today, only to the decoder that consumes input and produces output, trained as a standard language model. Okay, so this is what we talk today about. And they use it for writing Wikipedia pages as summarization tasks. So the task was, well, can you, given multiple documents, can you summarize it and that it looks like a Wikipedia page? It was a task back then. But the main architectural things was they dropped the encoder for the input because they said, well, if I drop the encoder, I save some parameters of the whole encoder. I don't have to, because there's so many attention heads, so many project matrices. So I don't need it. And also I can just train it autoregressively completely, end to end. I'm gonna just train it pre-train it on language modeling, and the actual task, the summarization, will also be like language modeling. So this was one thing they proposed before GPT-1, which then, like the same year basically, was adapted from the previous paper from Liu et al. And again, they adapted this decoder-only transformer. They didn't call it GPT back then. It was called generative pre-training, and I guess this in a later version of GPT where the GPT comes from. So they didn't call it GPT. There was like a decoder model. And the pre-training was done as a language modeling, so predict the next token in a sequence. And they added like an extra final layer for any given task. So remember we had BERT, and for the BERT, it learns encoding for each token. There was a special token for CLS, and there was special tokens for somewhere in the middle, and you would add some extra final layers for your final task, which you can sort of fine tune as well. So they did this here as well. So they add like a extra final layer for the final task, which could be like several, what is that? Text classification, language modeling as well, maybe summarization. I'm not sure. I mean, there were 12 different data sets they tried. So they pre-trained the thing on this books corpus data set. So 7,000 unique books was some sort of tens of millions of tokens, which looks small now, but back then it was maybe a big thing. And the actual architecture details was 12 decoder layers. So we have this decoder layer, they have 12 of them, and each of them had like 12 attention heads, and the embedding size some number. So some sort of parameters, it was decently big, back then. And just by this language model pre-training and then fine-tuning on this task, they on these 12 data sets, they improve on 9 of them, like the better results on state of the art. So different metrics, accuracy and classification, or stuff like that. So it was great, because the only thing you need is pre-training as a language model. You don't need more. You don't need a lot of training data for this task. You just need a lot of text for pre-train your language model, and then fine-tune on your task where you have a few data sets. So this was GPT-1. After that came GPT-2. So actually these papers were never published as this was a technical report. So no conferences, and OpenAI did publish these papers as a technical report. There was no peer review. And if you look into these papers, there are some details missing or something like, this is not like super detailed, but still they did publish some papers. If you look at paper about GPT-3, there is basically zero about the architecture. I mean, in GPT-1, they talk about the architecture a little bit. In GPT-2, they said like, well, we use GPT-1 architecture, just made it bigger. So we just had, 48 decoder layers and 16,000 embedding size, 1,600 embedding size. They didn't talk about the attention heads actually at all in the paper. So anyway, they said like, well, we took GPT-1 from the previous paper and make it just bigger, period, end of day. Training as language modeling. They changed the training from this books corpus, which turned out to be interesting, but maybe small. And what's bigger than books is the internet. Right? So they took the internet, but if you take the internet, you can take the internet, by the way. Everybody can download the internet. You know that? Do you know command crawl? Have you heard of that? Okay, that's interesting. Okay, so if you ever need to crawl the internet, don't do it. Somebody did it for you. So command crawl has been running for, I don't know, like maybe 10 years now. And every month they crawl the internet, billions of pages, and store it on AWS S3. And then you can access it in there. And if you have enough resources, you can download the internet. It's just maybe 100 terabytes is each crawl, maybe more now. I mean, it used to be, I worked with it like a couple of years back. It's maybe like 30, 50 terabytes. So it's big, but you can, basically all the HTML pages. So if you scrape the internet and run GPT on that, it will learn many bad things, because the quality of internet, so to say, like, it's not good in terms of like language quality. So what they did here is not to use the command crawl. Excuse me. Not to use the command crawl, but they scraped the internet by themselves. So OpenAI scraped it. And they say, well, okay, let's look at Reddit. Let's look at the links which are coming out of Reddit. And if the post at Reddit had at least some 3 of these karma points, whatever it means, some sort of like quality. So it means somebody maybe read this page, which was linked from Reddit. And if you read it and give point, it means like there is certain quality. So it's not completely crap. So there's something useful here, and maybe 3 people said like, I like that. So it's like it gives some quality, which is sort of like, getting sort of quality label data for free, right? I mean, somebody else did read the internet for you, and you just use this information to filter your data. So they filter data and ended up with 8 million documents in total. And it just worked much better than GPT-1. What do you think?
Right, but the requirement point seems pretty low, honestly. I would assume that every bot that spans some kind of trash link also easily reaches at least requirement point.
So, okay, yeah, this is 2018, 2019, and a heuristic they choose. I mean, you cannot reproduce it now because the internet has changed. But at least they said where the data is coming from. You know, if you look at GPT-3 and GPT whatever 3.5, there's zero information about where the data comes from. I mean, of course, it's some crawl, who knows what. Here they at least said, yeah, well, we use the links from Reddit. And so this is the evolution of GPT models, or to say like decoder-only models, which is nowadays, I guess, the more popular or more sort of spread way of using transformers for modeling. So all these big models nowadays, like Bloom, GPT, Llama, and all these thousands of others, they are based on this decoder-only model. So there are others who are encoder-decoder like T5, but they're just not really in a fashion right now. So, well, things might change, right? I mean,
state of the art or more.
Might be, yeah. Anyway, so there's a zoo of models. There's thousands of them. Everybody wants to have their own. Doesn't matter. What's interesting about GPT-2, and we'll talk about it next week, is this sort of prompting and few-shot learning and in-context learning. So we'll talk about it next week, but well, after the Christmas break, because it came with a new paradigm of how you work with language models without fine-tuning. But that's it for today. So a short recap. Well, there is no recap. Okay, so I should do some recap. Yeah. So GPT is a transformer model, only decoder, and the trick it works is this masked, sort of say masked language modeling. So this mask in a self-attention head, which prevents you from looking into the future, and just basically you can train it as a language model on tons of data. Having said that, I would say that's it for today. Have a great Christmas holidays. Happy New Year, and I'll see you sometime in January.